For this lesson, we're actually going to be taking a look at dot product again. We're just going to be looking at it in a slightly different way. In the previous lesson, we took a look at dot product of geometric vectors, which meant we were focusing on the idea of triangles and the angles between the vectors. Now we're going to be taking a closer look at components. Now, when we talk about dot product, we're going to be making use of both of them. The geometric and the algebraic interpretations of dot product are interchangeable, and sometimes we will shift from one to the other, and you'll see that happening. For this first one, we're given the vectors a and b, which can be represented in component form or can be represented in terms of the basis vectors. In this case, I'm going to make use of the basis vectors, and hopefully you'll see why it's particularly convenient in what I'm about to do here. So the vector a, I'm going to rewrite as the x component of a multiplied by the I vector plus the y component of a multiplied by the j vector. And I take the dot product of that with b, which is bx multiplied by the I and by multiplied by the j vector. As we discussed in the previous lesson, I can expand this very much the way I would do a binomial expansion. So essentially I'm going to make use of FOIL, first, outer, inner, last. And all I'm really doing there is the distributive property. That's where FOIL comes from. So in this case, my first terms, I end up with, I'll do the scalars first, so that's ax times bx, and then the vectors, but the vectors aren't a multiplication, the vectors are a dot product, so that's going to be I dotted with I. And then the outer terms are going to be axi with byj, so that's going to be plus ax by, and then the dot product part is I dotted with j. The inner part is going to be plus ay and bx, and then the dot product is going to be j dotted with I. And then finally the last two terms are going to be ay by, and that's going to be, the vector part is going to be j dotted with j. So now that I've done that, let's take a look at what happens with my vector components. We have a few vector components, and I'll just address them over here. We have I dot I, but we learned previously that any vector dotted with itself is simply equal to the magnitude of that vector all squared. But the magnitude of the vector I is equal to 1, so this is just equal to 1 squared, that's equal to 1. So this value just becomes 1. We also have an I dotted with j. And in this case, the thing I want you to remember is that I is perpendicular to j. So that's something we want to keep in mind. I and j are orthogonal, they're the basis vectors, but that means that the angle between them would be 90 degrees, which means that I dot j is equal to 0. So this is going to be 0. And the same holds true for j dot I, that's going to be 0. And j dot j is going to be, that's a unit vector, so that's going to be the magnitude of j all squared, which is simply equal to 1. So now when I simplify this, I end up with ax bx, ax bx times 1, ax by times 0 is just 0, ay bx times 0 is just 0, and then ay by. So in taking the dot product, when I represented these vectors in a component form, I just ended up multiplying the x components together, and I multiplied the y components together, and then I added the result of each of those two multiplications. And that's it. That's the algebraic definition of the dot product. So in R2, the algebraic definition is multiply the x coordinates together, multiply the y coordinates together, and then add the results. In R3, we multiply x coordinates, y coordinates, and z coordinates, and then add the results. So a simple little example here just to illustrate this. A dot B is equal to, I'm going to take the x components and multiply them together. So that's going to be -1 times 2 plus the y components, which is 4 times 1, plus the z components, which is 6 times -3. So this is my x, y, and z. This was my x, y, and z. And so by multiplying those together, I end up with -1 times 2 is -2, plus 4 times 1 is 4, plus 6 times -3 is -18. And so overall, I end up with -20 plus 4 is -16, which is a much quicker way. If you have components, that's far faster than having to figure out the angle between them, figure out the magnitudes of the individual vectors, only to end up with this fairly simple result. So this new approach, dealing with the dot product algebraically, is a real shortcut depending on the information that we have. Now, what about this? I'm given two vectors in component form, and I want to know the angle between them. So the thing I want to keep in mind here, as I said, the definition of the dot product has not changed, which means the geometric definition is still applicable. It's the magnitude of A times the magnitude of B times the cosine of the angle between them, and we want to know the angle between them. The only difference is now I'm actually going to figure out A dot B as well. I could do all of this together, but it would make for a fairly large and long expression, so I'm going to do one piece at a time. So let's figure out this part. So I'm going to do this part first, then I'll do my magnitude, then I'll do my magnitude, and then when I'm done that, I will put it all together. So let's go ahead, do part one, which is I'm going to do my A dot B. And that's equal to, I'm going to take the x components, 0 times 2, plus the y components, 5 times 4, plus the z components, 7 times 6, and that's 0 plus 20. Let's go ahead and write it out. 0 plus 20 plus 42, and so we end up with 62. That's my A dot B. Step 2, the magnitude of A, that's equal to, I square the x component, I square the y component, I square the z component, and then I take the square root of the whole thing, and that ends up being the square root of 25 plus 49, and that is equal to 74, the square root of 74. Similarly, the magnitude of B is equal to 2 squared plus 4 squared plus 6 squared, all square rooted, and that is equal to 4 plus 16 plus 36, all square rooted, and that is equal to 20 plus 36 is 56. Now it turns out you don't have to go to this next step, but it turns out that 56 is actually equal to, what is that, 4 times 14, I think. 8 times 7, 4 times 14, so that's 2 root 14. We could also write it that way, but do we really gain anything from there? We're going to be doing a calculation where we're going to end up putting this in our calculator. We're not going to be working with exact values when we come up with our angle theta. So this is really not an important step. This is an intermediate calculation. And then finally, for step 4, I'm going to put all of this together into my original equation, that A dot B is magnitude of A, magnitude of B, cosine of theta. And actually, it makes sense to simplify before we put any values in here. So I'm going to divide both sides by magnitude A times the magnitude of B. And I could even go further, and I think I'll do this in one step, which means I'm going to say theta is equal to the inverse cosine of, but now I'm going to fill some things in. So what was A dot B? We found that to be 62. So I'll fill that in here. 62 over magnitude A, which was root 74, magnitude B, which was root 56, and then we get theta is equal to. Now you have to be careful here. Actually, you know what? I'm going to do this the way we would do this if we were doing a trigonometry unit, because really we have to keep these things in mind no matter what it is that we're doing. So in this case, my related acute angle is equal to this, so that ends up being the cosine inverse of this works out to be approximately 15.6 degrees. And then from here, normally what we would do is we'd go to the cast rule. And we would say, okay, well, this was a positive value, so where is cosine positive? Cosine is positive in quadrant 1 and quadrant 4. But the thing you need to remember is that when we talk about the angle between two vectors, the maximum angle between two vectors is always going to be 180 degrees. Because if I have two vectors that are, let's say, like that, that's approaching 180 degrees. If I go to the other side of 180 degrees, well, then it's actually more convenient to measure the vector from here. So for that reason, we're going to reject our quadrant 4. Now, if you thought all of this through and you just went ahead straight to theta, okay, that's fine, because it turns out in this case that theta is 15.6 degrees. But I want you to understand, it's not as if we're throwing away any of the things that we've done in the past. For example, the idea of related acute angle, the idea of the cast rule. It just turns out in this case that we don't need to worry about that because of the geometry. If I go to greater than 180 degrees, I just measure my angle from the other direction. So that is our final answer for this one. The angle between those two vectors is 15.6 degrees. Now I'm given two vectors, and I'm being asked for what values of these vectors, for what value of k in this vector do we end up with something being perpendicular? Well, don't forget that perpendicular, to have something perpendicular means that the vectors u dot v have to be equal to 0. That's the definition in terms of the dot product. That's one of the results we get from the dot product. So I go ahead and do my algebraic interpretation of the dot product. Says take the x coordinates and multiply them together, plus take the y coordinates, that's where the k is coming in, and multiply them together, plus take the z coordinates, or z, I shouldn't say coordinates in this case, it's actually components. These are components of a vector. So I take the x components, the y components, and the z components. I multiply them together, but I can actually create an equation here and set that equal to 0 because I've been told the vectors are supposed to be perpendicular. So I end up with negative 3 here, plus 3k, plus 8 is equal to 0. So I'm going to leave my 3k on this side, and then I have 8 minus 3 is equal to 5, but I bring that to the other side, so that becomes negative 5. And so dividing both sides by 3, I end up with negative 5 over 3. And I only ended up, even though it said for what values, it turns out there's only a linear equation formed, and so we end up with k equals negative 5 over 3. And that is it for this lesson. Fairly brief. Remember, this is the second lesson dealing with dot product, so all we're really doing is looking at dot product from a slightly different perspective. The two together, the geometric and the algebraic interpretations, make dot product actually a very powerful tool for dealing with vectors.